Greetings, inquisitive minds. As the cosmic wind whispers through the silence, and the distant nebulae paint their eternal portraits across the canvas of night, we embark on another journey into the profound. Tonight, we delve into the very fabric of existence, exploring the unseen forces that sculpt our reality at its most fundamental level, the dance of electrons within atoms and molecules. It's a tale of remarkable ingenuity of how we began to tame the quantum realm. Settle in, find your focus, or let these concepts gently guide you into the deep. And if this exploration resonates with the curious corners of your mind, a simple like a thoughtful comment or a shared whisper with a friend would mean the world. Now let us begin. The universe, in its grand design, often presents us with puzzles that seem, at first glance, insurmountable. From the vast expanse of galaxies to the intricate dance of subatomic particles, every layer of reality holds mysteries waiting to be unraveled. Among these profound enigmas, few are as persistently perplexing or as fundamental as the behavior of the electron. Imagine, if you will, an electron. Not merely a tiny speck, but a quantum entity existing in a realm where the rules of our everyday experience simply do not apply. It's a world of probabilities, of wave functions, of simultaneous existences. For scientists, especially those delving into the atomic and molecular scales, understanding how these minuscule, often elusive, particles behave is not just a matter of academic curiosity. It is the very foundation upon which our understanding of matter itself is built. Electrons are the architects of chemical bonds, the carriers of electrical current, and the silent orchestrators of light and energy interactions. Without a profound grasp of their behavior, we would be blind to the true nature of materials, unable to predict their properties or design new ones. Yet, capturing their essence, pinning down their movements and interactions, is a task fraught with complexity. Consider an atom, a seemingly simple structure with a nucleus at its core, orbited by electrons. Now, scale that up to a molecule, a complex arrangement of multiple atoms, each contributing its own electron cloud. The sheer number of electrons and their constant, intricate interactions with each other and with the atomic nuclei creates a computational nightmare. Each electron exerts forces on every other electron, a delicate interplay of repulsion that dictates the molecule's overall shape, stability, and reactivity. This is not a simple game of billiards, where balls collide predictably. Instead, electrons are not just particles but also waves. They don't occupy fixed orbits. Rather, they exist in probability distributions, their exact location unknowable, their interactions governed by the strange and beautiful laws of quantum mechanics. The standard approach to describing such a system, particularly one with many interacting electrons, would involve solving the Schrödinger equation. This iconic equation, a cornerstone of quantum mechanics, provides the mathematical framework for describing how quantum systems behave over time. However, for anything beyond the simplest systems, say, a single hydrogen atom with its lone electron, the Schrödinger equation becomes practically intractable. The number of variables and the complexity of the interactions explode, rendering an exact solution impossible even for the most powerful supercomputers. Imagine trying to map every single ripple on the surface of a vast, stormy ocean, and then trying to predict how each ripple would affect every other ripple, all simultaneously. This is a rough analogy for the challenge of understanding interacting electrons. Each electron is a ripple, and their collective behavior shapes the entire ocean. This is why, for decades, the quantum realm, despite its profound importance, remains stubbornly out of reach for detailed, predictive analysis of complex systems. Scientists could understand general principles, but the granular details of electron behavior in, say, a protein molecule or a novel superconductor remained largely a black box. This inability to accurately model and predict electron behavior was a significant bottleneck in many fields, from materials science to biochemistry. The problem, at its core, lies in the nature of electron-electron interactions. These are not simple pairwise forces. Electrons are identical fermions, meaning they're indistinguishable and obey the Pauli exclusion principle. No two electrons can occupy the same quantum state simultaneously. This leads to intricate correlations in their movements, beyond simple electrostatic repulsion. Their quantum mechanical wave functions overlap and influence each other in ways that are deeply non-trivial. To accurately describe a system of many interacting electrons, you would theoretically need to consider a multi-electron wave function that depends on the coordinates of every single electron. For a system within electrons, this wave function would depend on 3 in spatial coordinates plus n spin coordinates. For even a modest molecule, n can be in the tens or hundreds, leading to a truly astronomical number of variables. Visualizing such a function, let alone solving an equation that describes its evolution, is beyond human comprehension and computational capacity. This formidable challenge presented a critical roadblock in quantum chemistry and condensed matter physics. How could we accurately describe the electronic structure of complex systems, predict their properties, and ultimately engineer new materials if the fundamental building blocks, the electrons, remained so elusive? The scientific community desperately needed a way to simplify this gargantuan problem, to find a shortcut that preserved the essential physics without drowning in an ocean of mathematical complexity. They needed a method that could capture the collective behavior of electrons without tracking each one individually, a conceptual leap that would transform the landscape of theoretical chemistry and material science. This urgent need set the stage for one of the most elegant and impactful theoretical developments of the 20th century, a breakthrough that would eventually earn its creators a Nobel Prize and fundamentally reshape our ability to understand the quantum world. The dream was to find a way to describe the system using something much simpler than the multi-electron wave function. What if, instead of knowing the precise quantum state of every single electron, we could describe the entire system by just knowing the electron density? The electron density, a simpler concept, tells us the probability of finding an electron at any given point in space. It's a three-dimensional function, independent of the number of electrons, and it intuitively captures where the electrons are concentrated within an atom or molecule. This idea, seemingly straightforward, represented a radical departure from traditional quantum mechanics. It suggested that perhaps all the intricate information about the system's energy and properties could be encoded within this much simpler quantity. But could it truly work? Could the complex dance of interacting electrons, governed by the formidable Schrödinger equation, be reduced to a picture of non-interacting particles, effectively simplifying the problem to an astonishing degree? This question, this profound riddle of how to tame the quantum complexity of electrons, would be at the heart of a revolutionary new approach, one that would redefine our understanding of matter itself. The challenge was immense, but the potential rewards were even greater, a pathway to unlock the secrets held within the very fabric of the universe, one electron at a time. This would be the genesis of the Kohn-Sham equations, a brilliant stroke of genius that dared to imagine a fictitious, non-interacting universe to shed light on our own. Welcome back, weary travelers of the cosmos, to another journey into the profound depths of scientific understanding. Tonight, we drift further into the intricate world of quantum mechanics, where the very fabric of reality takes on a shimmering, elusive quality. Last time, we grappled with the inherent enigma of the electron, its restless dance, and the seemingly insurmountable challenge of truly comprehending its behavior. We acknowledged that directly observing and calculating the interactions of countless electrons within an atom or molecule is a task that would overwhelm even the most powerful supercomputers, rendering our quest for perfect prediction almost futile. But humanity, in its boundless ingenuity, often finds ways to navigate the seemingly impossible. And so, we arrive at one of the most elegant and profound deceptions ever conceived in the annals of science, the Kohn-Sham equations. Imagine, if you will, a magician who makes an entire troupe of acrobats vanish, only to reveal their positions perfectly by observing the single shadow they cast. This, in essence, is the subtle brilliance of the Kohn-Sham approach. At its heart, the Kohn-Sham system is a masterful simplification, a clever trick that allows us to sidestep the intractable complexity of interacting electrons. Instead of wrestling with every single electron's intricate dance with every other electron, Walter Kohn and Kohn-Sham, in 1965, proposed a fictitious universe. In this imagined realm, electrons do not interact with each other directly in the same chaotic way as they do in our reality. They are, for all intents and purposes, independent, non-interacting particles. Now, you might wonder, how can a system built on such a fundamental falsehood yield accurate insights into the very real and highly interactive world of quantum mechanics? The genius lies in the same density principle. The Kohn-Sham system, despite its fictitious nature, is carefully constructed to produce the exact same electron density as the real, interacting system. This electron density, remember, is the probability of finding an electron at any given point in space, and it turns out to be a surprisingly powerful descriptor of a material's properties. It's like saying, even if the acrobats are imaginary, if their combined shadow perfectly matches the shadow of the real acrobats, then that shadow can tell us everything we need to know about the real performer's arrangement. So, while the electrons in this Kohn-Sham universe are non-interacting, they are not entirely free. They still move within an effective potential, a kind of invisible landscape that guides their fictitious journeys. This effective potential, often denoted as V_s or V_f, is the clever conduit through which the complexities of the real world are subtly introduced. It acts as a stand-in, encoding all the intricate electron-electron repulsions and quantum exchange correlation effects that are so difficult to calculate directly. Think of it as setting up a series of invisible magnets on a table. If you then roll a marble across that table, the path it takes will be influenced by those magnets, even though the marble itself isn't interacting with other marbles. The Kohn-Sham potential is those invisible magnets, shaping the paths of our fictitious electrons so that their collective probability distribution, their density, mirrors that of their real, interacting counterparts. The mathematical expression of this elegant deception takes the form of a Schrödinger-like equation for these non-interacting particles. It's an eigenvalue equation, describing the energy states of these fictitious electrons, much like the original Schrödinger equation does for real particles. The solutions to these equations are what we call Kohn-Sham orbitals, which are essentially mathematical wave functions describing the individual states of these non-interacting electrons within the effective potential. Each orbital, denoted by phi_i, has a corresponding orbital energy, epsilon_i. These orbital energies, in general, don't have a direct, straightforward physical meaning in the same way that energy levels in a hydrogen atom do. They are more like mathematical constructs, stepping stones on our path to understanding the real system. However, the sum of the squares of the magnitudes of these orbitals across all the electrons in the system precisely reconstructs the real electron density. This is the crucial link, the Rosetta Stone that translates the simplicity of the fictitious system into the rich complexity of the real one. The beauty of this approach is that solving for non-interacting electrons, even within a complex effective potential, is computationally far less demanding than solving for the myriad interactions of real electrons. It transforms a prohibitively difficult many-body problem into a series of much more manageable single-particle problems. The historical genesis of these equations is as fascinating as the science itself. As mentioned, Walter Kohn and Kohn-Sham introduced this groundbreaking concept in 1965 at the University of California, San Diego. Their work laid the foundation for what would become known as density functional theory, or DFT, a theoretical framework that has revolutionized our ability to predict the properties of materials at the atomic and molecular scale. For this profound contribution, Walter Kohn was rightfully awarded the Nobel Prize in Chemistry in 1998, a testament to the immense impact of this elegant deception. Now, let's peel back another layer of this ingenious construct and delve into the heart of the Kohn-Sham potential itself. Recall that the total energy of any system, in the language of density functional theory, can be expressed as a functional of the electron charge density. A functional, for those unfamiliar, is a function of a function. Instead of taking a number as input and returning a number, a functional takes an entire function, like our electron density, as input and returns a number, like the total energy. The total energy E of our system is essentially a sum of several components. There's the Kohn-Sham kinetic energy, T_s, which account for the motion of our fictitious, non-interacting electrons. Then we have the interaction with the external potential, V_xt, which for a molecule, for instance, represents the pull of the positively charged atomic nuclei on the electrons. Next, we encounter the Hartree energy, E_h, which describes the classical electrostatic repulsion between different parts of the electron cloud. Imagine two regions of negative charge repelling each other. That's the essence of the Hartree energy. Finally, we arrive at the most enigmatic, yet profoundly important component, the exchange correlation energy, E_xe. This term is the repository for all the intricate quantum mechanical effects that are not captured by the simple kinetic energy or classical electrostatic repulsion. It accounts for the Pauli exclusion principle, which dictates that no two identical fermions, like electrons, can occupy the same quantum state, and also for the subtle correlations in their movements that arise from their interactions. This exchange correlation energy functional is the only truly unknown term in the Kohn-Sham equations, and it is here that the approximations in density functional theory reside. The accuracy of a DFT calculation often hinges on how well this elusive exchange correlation functional is approximated. By varying this total energy expression with respect to the Kohn-Sham orbitals, while ensuring they remain mathematically orthogonal, we arrive at the Kohn-Sham equations in their full glory. This process reveals the precise form of the effective potential, V_ff, which guides our fictitious electrons. This potential is a composite entity, a masterful blend of several forces. It includes the external potential, V_xt, as we discussed, the pull from the atomic nuclei. It also incorporates the classical Hartree potential, derived directly from the electron density, representing the averaged electrostatic interaction. And then, crucially, it contains the exchange correlation potential, V_xe. This exchange correlation potential is the functional derivative of the exchange correlation energy with respect to the electron density. In simpler terms, it describes how the exchange correlation energy changes as the electron density changes at a particular point in space. It's the secret sauce, if you will, that allows the fictitious system to mimic the real one. It's important to reiterate that while the Kohn-Sham orbitals and their energies are incredibly useful mathematical tools, their individual physical meaning should be approached with caution. They are not direct measurements of real electron energies or positions. They are part of the elegant deception, designed to lead us to the one true physical quantity we care about, the electron density of the interacting system, from which all other observable properties can, in principle, be derived. The power of the Kohn-Sham equations and density functional theory cannot be overstated. From predicting the properties of novel materials, designing more efficient catalysts, understanding the mechanisms of chemical reactions, to even modeling biological systems, DFT has become an indispensable tool in countless scientific disciplines. It allows us to peer into the microscopic world, unraveling the mysteries of matter with a level of detail and accuracy that would have been unimaginable before its inception. As we conclude this segment, take a moment to appreciate the sheer intellectual elegance of this approach. Faced with a problem of overwhelming complexity, Kohn and Sham did not try to solve it head-on. Instead, they conjured a simpler, parallel universe, a sophisticated illusion that, by meticulously matching one observable quantity, the electron density, allows us to indirectly but powerfully access the secrets of the real world. In our next segment, we will delve deeper into the lives and contributions of the brilliant minds behind this elegant deception, Walter Kohn and Kohn-Sham. We will explore the intellectual landscape that gave rise to their groundbreaking work and further unpack the profound impact of density functional theory on modern science. Until then, let the gentle hum of the cosmos lull you into a state of focused contemplation as the phantom electrons of the Kohn-Sham universe continue their silent, yet profoundly insightful dance. As we delve deeper into the enigmatic heart of quantum mechanics, we encounter the brilliant minds that dared to gaze into its deepest complexities and emerge with tools to unravel its secrets. Our journey now leads us to the architects of insight, two scientists whose names are etched into the very foundation of modern material science and chemistry: Walter Kohn and Kohn-Sham. It was in the year 1965, at the University of California, San Diego, that Kohn and Sham introduced a concept that would revolutionize our understanding of electrons. They proposed a set of equations, now famously known as the Kohn-Sham equations, which brought a profound simplification to the bewildering problem of how electrons interact within atoms and molecules. Imagine, if you will, the bustling, chaotic dance of countless electrons within a material. Each electron repels every other electron, all while being simultaneously attracted to the positively charged nuclei. This intricate ballet of forces makes the direct calculation of their collective behavior incredibly difficult, a challenge that has vexed physicists and chemists for decades. The traditional Schrödinger equation, while fundamentally correct, became computationally intractable for systems with more than a handful of electrons. Kohn and Sham, with a stroke of elegant genius, found a way to sidestep this complexity. Their radical idea was to invent a fictitious system, a universe, if you will, where electrons don't interact with each other in the messy, complicated way real electrons do. Instead, these Kohn-Sham electrons move independently, each influenced only by an effective potential. The crucial, almost magical aspect of this fictitious system is that it generates the exact same electron density as the real, interacting system. Think of it like this. Instead of trying to predict the precise trajectory of every single raindrop in a storm and how each one impacts another, Kohn and Sham found a way to predict the overall shape and intensity of the rain cloud itself, using a much simpler model of non-interacting virtual raindrops. The end result, the rain cloud's density, is what truly matters for understanding its impact on the ground below. This introduction of non-interacting electrons, moving in a cleverly constructed Kohn-Sham potential, was the key. It allowed them to transform the formidable many-body problem of interacting electrons into a series of much simpler single-particle equations. These equations are, in essence, Schrödinger-like equations for our fictitious electrons, but with a unique potential tailored to mimic the effects of all the real interactions. The elegance of this approach lies in its ability to find the most stable arrangement of electrons. By solving these equations, scientists can determine the ground state electron density, which in turn reveals a wealth of information about the material's properties. From its conductivity to its chemical reactivity, from how it absorbs light to how it binds with other atoms. All of these emergent behaviors are rooted in the electron density, the very heart of the Kohn-Sham theory. The mechanism that links the fictitious to the real is the introduction of a functional known as the non-interacting kinetic energy, often denoted as T sub/sub. When this functional is integrated into the total energy expression for the system, and then subjected to a process called functional differentiation, it miraculously leads us to a collection of one-particle equations. The solutions to these equations are what we call the Kohn-Sham orbitals. These Kohn-Sham orbitals, represented by phi sub I slash sub r, are the mathematical descriptions of how our fictitious, non-interacting particles behave. They're the building blocks from which the electron density of the actual, interacting system is constructed. And the equation that governs these orbitals, the quintessential Kohn-Sham equation, looks something like this. It's an eigenvalue equation, a familiar form in quantum mechanics, where epsilon sub I slash sub represents the orbital energy of each corresponding Kohn-Sham orbital. The operator on the left side describes the kinetic energy of the fictitious electron and the effective potential it experiences. And from these orbitals, the electron density ρ, r, for an n-particle system is derived simply by summing the squared magnitudes of these orbitals. This seemingly straightforward sum is the bridge connecting the simplified, non-interacting world of Kohn-Sham to the complex, interacting reality. The profound impact of this work cannot be overstated. Walter Kohn's pioneering contributions, particularly the Kohn-Sham equations and his broader work on density functional theory, were recognized with the Nobel Prize in Chemistry in 1998. It was a testament to the power of theoretical insight to transform practical science. So, what exactly is this enigmatic Kohn-Sham potential that orchestrates the behavior of our fictitious electrons? It's the linchpin, the clever mathematical construct that ensures the non-interacting system faithfully reproduces the density of the interacting one. In Kohn-Sham density functional theory, the total energy of a system is expressed as a functional of the charge density. This functional is a sum of several terms. First, there's the kinetic energy of our fictitious, non-interacting electrons, T sub s slash sub. Then, there's the interaction of these electrons with the external potential, the attraction to the positively charged atomic nuclei, for instance. This term is integral d r asterisk 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 v sub ext slash sub asterisk asterisk r asterisk 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 rho r asterisk asterisk star. Following this, we account for the classical electrostatic repulsion between the electrons themselves, known as the Hartree energy, E sub H slash sub. This term describes the repulsion of an electron distribution with itself. And finally, the most crucial and most challenging piece of the puzzle, the exchange correlation energy, E sub Xc slash sub. This exchange correlation energy is where all the complex, non-classical quantum mechanical effects of electron-electron interaction are bundled together. It's a term that accounts for both the Pauli exclusion principle, which prevents identical electrons from occupying the same quantum state, and the intricate dynamic correlations between electrons as they move. It's the one term in the entire framework that isn't known exactly and must be approximated. The Kohn-Sham equations themselves are derived by a variational principle. We essentially seek the set of Kohn-Sham orbitals that minimize the total energy functional, under the condition that these orbitals remain orthogonal to each other. This minimization process yields a time-independent Schrödinger equation, but with a special scalar potential, the Kohn-Sham potential, V sub EFF slash sub R. This effective potential is not a simple, fundamental force. Instead, it's a composite of several contributions. It includes the external potential, V sub EXT slash sub R, the classical electrostatic potential arising from the electron density itself, and critically, the exchange correlation potential, V sub Xc slash sub R. The exchange correlation potential, V sub Xc slash sub R, is defined as the functional derivative of the exchange correlation energy with respect to the electron density. This term, and the corresponding energy expression for which it derives, are the only truly unknown components in the entire Kohn-Sham approach. The accuracy of any density functional theory calculation hinges almost entirely on how well we approximate this exchange correlation functional. Entire careers are dedicated to developing better and more robust approximations for E sub Xc slash sub. Now, a fascinating nuance to consider. The orbital energies epsilon sub I slash sub derived from the Kohn-Sham equations generally hold little direct physical meaning on their own. Unlike the energies obtained from the true Schrödinger equation, which correspond to observable energy levels, the Kohn-Sham orbital energies are primarily mathematical constructs designed to help us calculate the total energy and electron density. While they can sometimes approximate ionization potentials or electron affinities in specific contexts, they're not, in general, direct measurements of physical energy levels. The total energy of the system, E, can be related to the sum of these orbital energies, but also involves subtracting the Hartree energy, adding the exchange correlation energy, and then further subtracting a term that corrects for the double counting of interactions that occur when summing orbital energies. This complex relationship underscores the fact that the Kohn-Sham orbitals and their energies are part of a self-consistent computational framework, rather than direct representations of physical observables. The journey from the bewildering complexity of interacting electrons to the elegant simplification of the Kohn-Sham equations is a testament to the human intellect's capacity for abstraction and problem-solving. It's a powerful reminder that sometimes, to understand the deepest truths, we must first construct a clever, fictitious universe that mirrors reality in just the right ways. And it is this very insight that has propelled density functional theory to become one of the most widely used and indispensable tools in modern science, allowing us to predict and engineer materials with unprecedented precision. Having journeyed through the subtle realms of quantum mechanics, from the enigmatic dance of electrons to the elegant scaffolding of Kohn-Sham's fictitious universe, we now arrive at the heart of their revolutionary insight, the Kohn-Sham potential. This isn't merely a mathematical construct. It is the brushstroke on the quantum canvas, the unseen force that shapes the electron density of all matter, a silent conductor orchestrating the universe's most fundamental interactions. The Kohn-Sham potential is, in essence, the localized effective external force within which our fictitious, non-interacting electrons reside. Remember, the true genius of Kohn and Sham was in realizing that even without directly modeling the bewildering interactions between countless real electrons, we could still arrive at the same electron density by using a simplified system of independent particles. The Kohn-Sham potential is the key to making this astonishing equivalence possible. Imagine a grand cosmic theater where countless tiny, energetic beings, our electrons, are buzzing and interacting, pushing and pulling, creating an incredibly complex, vibrant, and ever-changing tapestry of energy. The traditional quantum mechanical approach attempts to describe each individual interaction within this chaotic dance. It's like trying to predict the exact path of every single snowflake in a blizzard. But the Kohn-Sham approach offers a different perspective. It says, what if we could simplify this blizzard? What if we could imagine a calm, organized flow of these energetic beings, each moving independently, but collectively producing the exact same shape of the overall cloud as the real, chaotic blizzard? The Kohn-Sham potential is the invisible wind that guides these imaginary snowflakes, causing them to settle into precisely the same distribution as their wilder, interacting counterparts. Formally, this potential, often denoted as V_F or V_S, is what transforms the Schrödinger equation from an intractable problem of many interacting particles into a soluble set of one-particle equations. These are the Kohn-Sham equations themselves, resembling the simple Schrödinger equation we're familiar with, but with this clever, effective potential in place. The solutions to these equations are what we call the Kohn-Sham orbitals. And from these orbitals, we can directly construct the electron density, the very quantity that density functional theory hinges upon. The elegant beauty lies in this transformation. By solving for these single-particle orbitals under the influence of V_F, we obtain the system's electron density, ρ, which then unlocks all the macroscopic properties of the material we're studying. It's a profound shortcut, a way to peer into the quantum realm without getting lost in its infinite complexities. Let's unpack the components of this Kohn-Sham potential. because within its structure lies a deeper understanding of its power. The effective potential is a sum of several crucial terms, each contributing to its ability to mimic the real world. First, there's the external potential, often written as VNFXT. This is straightforward. It represents the influence of atomic nuclei on the electrons. In a molecule, it's the attractive force exerted by the positively charged protons in the atoms. This is a known quantity, a constant in our calculations, reflecting the fixed positions of the atomic cores. Next, we encounter the Hartree potential, often called the Coulomb potential. This term accounts for the classical electrostatic repulsion between electrons. Even in our fictitious non-interacting system, we still need to acknowledge that electrons, being negatively charged, repel one another. The Hartree potential captures this average, classical interaction, treating the electron density as a smeared-out charge cloud that pushes back on itself. It's an approximation, yes, but a crucial one, capturing the bulk of electron-electron repulsion. But here's where the true magic and the lingering challenge of DFT comes into play. The external potential and the Hartree potential are relatively easy to calculate. They are well-defined and can be determined with precision. However, these two terms alone are not enough to perfectly reproduce the true electron density. They miss the subtle, intricate quantum effects that arise from electrons being indistinguishable fermions, obeying the Pauli exclusion principle and experiencing quantum correlations. This brings us to the final and most elusive component of the Kohn-Sham potential, the exchange correlation potential, often denoted V_XC. This is the enigmatic heart of density functional theory. It's the term that lumps together all the complex, non-classical quantum interactions, the exchange effects arising from the indistinguishability of identical particles, and the correlation effects, where the motion of one electron is subtly influenced by the instantaneous motion of others, going beyond simple average repulsion. The exchange correlation potential is derived from the exchange correlation energy functional, E_XC. This functional is, in essence, the correction factor, the unknown piece of the puzzle that makes the entire Kohn-Sham framework work. If we knew the exact form of E_XC, density functional theory would be exact, capable of solving any many-electron problem with perfect accuracy. But alas, the exact form of E_XC remains unknown. This is why approximations are so vital in DFT. Scientists develop various approximations for E_XC, each with its own strengths and weaknesses, designed to capture these subtle quantum effects as accurately as possible. From the simplest local density approximation to more sophisticated generalized gradient approximations and hybrid functionals, the quest for a better E_XC is an ongoing frontier in quantum chemistry and condensed matter physics. The orbital energies, epsilon_I, that emerge from solving the Kohn-Sham equations are fascinating in themselves, though it's important to note that they don't always directly correspond to physically measurable energies of individual electrons in the same way that energies from the exact Schrödinger equation might. However, their sum, when combined with other energy terms like the Hartree and exchange correlation contributions, does lead back to the total energy of the system, providing a powerful means to calculate the stability and reactivity of atoms and molecules. The intellectual journey that led to these equations is a testament to scientific ingenuity. Walter Kohn and Liu Sham introduced this concept at the University of California, San Diego in 1965. Their brilliant reformulation of the many-body problem, reducing it to a set of manageable one-particle equations, revolutionized our ability to predict the behavior of matter at its most fundamental level. For this profound contribution, Walter Kohn was rightfully awarded the Nobel Prize in Chemistry in 1998, recognizing the transformative impact of the Kohn-Sham equations and the broader framework of density functional theory. So, the Kohn-Sham potential is not just a mathematical term. It is the embodiment of a conceptual triumph. It allows us to decode the intricate quantum canvas, unveiling the electron density, the very blueprint of matter, without having to individually track every brushstroke of interacting electrons. It is the bridge between the unimaginable complexity of the quantum world and the predictive power that fuels our understanding of everything from new materials to biochemical processes. As we conclude this exploration, remember that even in the face of nature's most profound mysteries, human intellect, guided by imagination and rigorous inquiry, can often find a simpler, more elegant path. The Kohn-Sham potential is a shining example of this, a fictitious guide leading us to genuine understanding, allowing us to continue our slow, deliberate decoding of the universe's grand design. As our journey through the elegant complexities of the Kohn-Sham equations concludes, remember that every step we take in unraveling these quantum mysteries brings us closer to a profound understanding of the universe, and indeed, ourselves. This knowledge is not just for the lab. It shapes the world around us in countless unseen ways. If this deep dive resonated with your spirit of inquiry, please consider liking this video, sharing it with those who seek similar cosmic whispers, and subscribing to join us for future explorations. What part of the quantum realm or the grand cosmos calls to you next? Share your thoughts in the comments below, and until our next adventure, keep observing, keep questioning, and keep vibing with science.